So, well, let's get started here, if I can. There we go. So really, the motivation for this work, about 5 years ago or so, I was working on a PhD dissertation that centered on understanding the PAI implications of overwing nacelles. So I wanted to have a powered engine model because I was concerned that the exhaust blowing over a supercritical wing would cause a lot of problems, and I didn't want to flow through nacelle, so I had to worry about that. In an academic environment, I started with SU2 because it's free and open source, which is the right price for students. And then after I started at NASA, I moved over to Cart3D. But the whole time I used OpenVSP for the geometry engine to model this whole thing. And so when I got started with Cart3D, the process for making a engine model or a power boundary condition model is you create some geometry, which for me is on my workstation, which is a Windows computer using OpenVSP. And then you take your VSP model, you export a trie file. Then Cart3D is, of course, on a Linux system. And I know all you Mac users will snicker at me, but I have to work between the two systems because our Linux are headless, so there's no VSP on there. So carry it over to Linux, create a Trix, or use the Trix command to create a tech plot file, bring it back to my Windows computer, find certain mesh cell numbers on the faces, in TechPlot, and then take that back to the Linux side. And there's a command called break tries that will find that cell number, and it will separate your watertight component where there's sharp edges. So if you think about like a 90-degree turn, it will find all the cells that are within that plane, and it will break them from the rest. Then once you have your broken geometry, you use Trix again to create a tech plot file, and then you can figure out which surfaces are your flow-through surfaces and which ones are your solid surfaces. Just a lot of steps. I wasn't very comfortable with all of this, especially going back and forth from Windows to Linux. It was kind of time-consuming, so I said, can I just do the whole thing in VSP and not have to worry about it? So we spent some time, and the answer is yes, basically. If you heard one of Rob's talks earlier about subsurfaces, right? OpenVSP has these subsurface features that will break out surfaces into subsurfaces. It tags them, and they'll create separate components automatically. And when I first started this, I had these really small gaps because I would say, hey, look, I want a subsurface. Oops, guess there's no right click. Right along, this inlet geometry here. But based on where my components were in the UV space, they wouldn't line up perfectly. So, for example, if I had, if my UV cross sections were every third of a number, so if I had cross sections 0, 1, 2, 3, 4, 0, 1, 2, 3, my cross section UV wise would be at 0, 0.3333, 0.666, and then 1. And you can't put a subsurface at exactly 1/3. It's an irrational number, so it doesn't make any sense. But I could get around this if I perfectly matched the UV coordinates with OpenVSP. And the way I did that was kind of padding the number of cross sections I had. And so this is kind of an overview of what the model ended up looking like here, where you have your spinner, your inlet. This inner surface here is actually a separate surface. So if you're doing your drag bookkeeping, this can go in kind of the engine makers typically count this towards their ram drag, whereas the external nacelle drag gets booked up with the airframe typically. Same thing with the inner parts and so on and so forth. Kind of covered this already, but in general with OpenVSP in the UW space, 0 is your first cross section. It's 0 indexed also. And then 1 is your last, right? So in UV space, your component goes from 0 to 1. It doesn't matter how big it is, if it's 10 feet or 100 feet. In UV space, it's 0 to 1 for the most part. Intermediate cross sections have a U or V coordinated as I over N. So again, if you have cross sections going from 0 to 4, you would have, I would say, 4 cross sections. It's really 5, but with the 0 index, that last one's 4. And so each cross section is at I over N. And as long as 1 over N is rational, you're fine. If it's irrational, you can't place subsurfaces directly on top of the cross sections. So it kind of limits you to how many subsurface or cross sections you can use. That should be cross section. 2, 4, 5, 8. It goes on, but you get the idea. And if you don't have exactly 16 or 20 cross sections, you can just add more cross sections to the start or the end in order to kind of pad the number of cross sections you have and get the UV spacing where you want it to be. And so if we look, the last chart that I have before I jump into a demo is this is what my geometry looked like. This is exported from TechPlot, so it's a little bit cleaner and highlighted. But I had 20 cross sections. That's 21, but it's numbered from 0 to 20. You can control the key areas and dimensions, right? So the inlet area, the exhaust areas, the maximum diameter of the nacelle, the highlight diameter and where all those are located. And for my example, I just used an axisymmetric nacelle for convenience, but certainly if you wanted a non-axisymmetric nacelle, either because you want kind of a droop or something like that, you can do that through skinning. And another feature here is I have blunt trailing edges on the aft part of the nacelle and kind of these cones here, and also the leading edge and trailing edge. So let's see. Oh, I guess the other note I'll make is, and we'll go through this, is getting this curvature right in the highlight region is pretty tricky, right? So you have to just be careful with your skinning in order to do this. But with that, that's the end of my chart. So I'll start walking through a demo here to that one, to go through here. So first, right, if we take a fuselage and add it just to really kind of highlight the UV spacing here a bit. There's a generic fuselage. It natively has, if you go to the cross sections, it has 4. So 0, 1, 2, 3, 4. And let's just add a blank and attach it in the UV space. And so it's at U equals 0. It's at the nose. If I move it to U equals 1, it's back there. If we put this at 0.5, it goes to the middle. Right, so that's nothing fancy. But if we cut out some of these, so now we only have one intermediate cross section, 0, 1, and 2. And if we look, that blank, which is right here, is still at U equals 0.5. And it doesn't matter where I move this cross section, that is U equals 0.5. It doesn't matter if that cross section is right next to the leading edge or if I move it all the way back to the trailing edge, that's where U equals 0.5. So U is 0. It's probably a quarter-ish around here. It's 0.5 right here, and it's 3/4, somewhere right there. So it's not linearly spaced, which can be frustrating if you were expecting that. But if you know that's a feature, you can use it really to your advantage on how to do this. And so the next step is here's a clipped view of my engine model. If you turn off the clipping, it looks like that. It's a watertight single component stack. So I use the stack feature here. If we turn clipping back on so you can see the internals. There we go, making sure my view is right here. Let's just, that'll do. So I'll just walk through this here fairly quick. If we go to the first cross section, it's just a point. Right, the second cross section is also a point. Right, so this is an example of padding. I have 2 points at the leading edge. There's no point in having 2 points to start out your geometry, but it was necessary for me to get 20 so I could do simple math. Same thing. This next one is this intermediate circle. That's just a padded subsurface. I could have, or cross section, could have made that a point also. We go out and I have this blunt spinner. I did that because when I was going to grow cells off of this geometry for SU2, I didn't want a sharp point and have kind of the tricky mesh cells that came with that. So I blunted it a little bit. And then just walking through, right, it comes out to the next one is here, which is the start at the inlet. And then also what I did is I put a subsurface here, the inlet inner diameter. And if you notice that the cross section is 0.2, this is cross section 4, so that's 4 out of 20. And it's perfectly exactly there, lined up. If we look at this cross section skinning wise, the angle comes in along the x-axis, so at an angle of 0, and it goes out at 90 degrees to the x-axis. So you have this perfectly flat inlet face. If you go to the next cross section 5, it comes in at 90 and it goes out at 180, so it's going in the negative x-axis. So here's how you define your inlet. And again, there's another subsurface on the outer diameter. So when this gets exported, this inlet face is its own face. And there's no need to worry about what number it is. It's number 2. Number 1 is the spinner. Number 2 is this one. VSP just orders them kind of in a UV coordinate number. Let's see, the next cross section is right here at the highlight. And this is where you have to play with the skinning and the diameter to look kind of how you want. What I also did, and I'll show you in a meshing example here in a minute, is I put another subsection here at the highlight so that when I export this into a meshing tool like Pointwise or something, it will give me a connector here that I can control the spacing there. That way, right, Brandon talked about in the last presentation, you want to make sure you have enough refinement on your leading edge. You can get that by putting a cross section there. Yeah, walking through. Next one is kind of the max diameter cross section right here. You could move this forward or after, make it bigger or smaller to change the nacelle shape, or if you had some kind of optimizer, you could probably try and run that through. Let's see, go into the back. Here's my blunt trailing edge. It's just a very thin trailing edge on the back, and then it doubles back on itself right there. And I put another subsection here so that I can separate this inner surface from the outer surface for that thrust drag bookkeeping issue. And then I moved it here. And you can, right, obviously, if you want to model more of the internals of the engine, you could move this surface back further to here, but I didn't want to, so I just moved it here, save some cells and things. And yeah, and then it's just repeat the process. It comes out through here. Oh, there is one more feature I want to talk about. Here's the input, the exhaust flow, the bypass flow, I should say. And I put a cross section here, you can see. And it's kind of annoying because it broke up this nice smooth surface that I wanted to have on the nozzle for the core. But doing this allowed me to control the diameter right here. And if I were to line up the view right, this cross section is right located in line with this upper one. So you take the diameter here of 0.918, and if you took the diameter of this point here, you can easily find the nozzle area for your flow. And if you're doing some kind of inviscid solver, you really only need to know the area of your boundary condition, so you know how much back pressure to apply there, and then the area of your nozzle, so you can control the Mach number there. And with those two things, you can pretty much set everything up. Viscous solvers are a little bit trickier, but Cart3D was inviscid, so I didn't have to worry about that for a while. And then after that, yeah, same process for the core. I put another cross section here to give the core nozzle area. And then I think in the back I have a few more cross sections to pad it, so I got 20. Yeah, so then from here, right, if you were to run comp Geom, you would get this. I foiled. So when I saved it, it did not work properly. I don't know. I can run this again and show you what it looks like. It'll take a few seconds to load. I guess it gives me the opportunity to say that when I started this, it never works like you think it's going to. Or did I think I comp Geom the wrong thing. Let's try this. Show comp Geom. All right, let's try this one. When I ran through this inviscidly, right, like I said, just kind of eyeballed most of this geometry. It's more or less right, and every engine looks more or less like this, right? The diameters will change, the max thickness will change, the length to inlet diameter, will change, but fundamentally it's the same. When I ran it viscously, I did get separation coming off of this inlet lip because it wasn't designed terribly well. It was just kind of eyeballed, and inviscid calculators don't care. There's no separation. Viscous calculators do care. All right, so here's the comp Geom. You could stick this straight into Cart3D and it would run very well. Yeah, you probably should up the tessellation a little bit, but Cart3D is pretty insensitive to that. Make this geometry, you run it, you can test it, you can then go back and, if the areas don't line up to what you thought they were or something, you can just change it and put it straight into Cart3D and run. Very quick. If you didn't use the subsurfaces, this whole thing would just look like this, which is, one single component, and it's not broken out, and it's not at all what you want. So you need the subsurfaces for that. Once you have this geometry, you can go file export and export as a untrimmed IGES. You want to split surfaces on the UW constraints. Units or meters, sure, why not? Let's just cancel that because I've already done that and I don't want to risk breaking it. But from here, right, so if you have that, you can go into your favorite meshing tool. For me, that's Pointwise. I know Brandon's a big CGT guy, but I'll just take this. Convert from file. It always gave me this warning, can't convert 56 entry entities. I don't know if that's a VSP thing or a Pointwise thing. So really quick on how to mesh this in like Pointwise. It's select databases, select all, and just turn this into a what should be a single water type model. But if you go down, you'll look, it's not a single one, there's 4, and it comes down to kind of this region back here. There's a few surfaces that didn't play nice. So we can just take the main one and put it in its own layer and turn it off. And now we can go look at the back of the engine. And I know from experience that these ones back here are kind of in the 2nd, 3rd, and 4th quadrant. Doesn't matter though, we'll just get rid of them. This is, those blunt surfaces at the nose and the tip of the engine. If I have a quarter of an engine now, I can turn this layer back on. It's a quarter of a water type model. You should follow your best meshing practices, but we'll just put 50 nodes on every connector here. Highlight all these and make a mesh. There. So we now have a structured mesh across the entire engine. You can go and apply your best practices as you want, right? If you decide that you don't want quite that many nodes along here, let's deselect that. We'll select connectors. You can always change this to 25. And because it was a structured mesh, all of the radial components here need to be the same. I missed these two, so we'll change these to 25 also. Have a nice mesh. Oh, I mean, it's not a nice mesh, but it looks good. If we notice here, this is not near refined enough near the leading edge, but because we put a constant U surface here, or a subsurface, we can control the spacing. Just pick these connectors there, set a spacing of 1 centimeter, why not? And that'll pull points forward. And now we can really control the spacing there. Again, probably not fine enough for what you want, but for a 5-minute demo, this works pretty well. So if you like that mesh, there's a quarter of your engine. You can just copy it and paste it. And it'll ask you how you want to paste it. So let's mirror it about z equals 0. Sure. Okay. Let's do that again. We'll just copy and paste. And this time we'll mirror it about y equals 0. There. So now we have a full engine. It's all meshed how you like. The only thing that's not right is, it couldn't make a structured mesh on this surface because there's only 3 connectors. So what we can do is just make sure I don't get any connections in there. Yeah. Delete those 4, and Pointwise is smart enough to know how to connect a circular mesh. And there. So this whole thing would be a structured mesh if you wanted it. If you wanted to use an unstructured, it's pretty easy. You can either, the lazy way, I suppose, would be to go in here and just diagonalize it. And we'll hide the original mesh. And there, so now it's an unstructured mesh, if that's what you wanted. You could also use, T-Rex, and there's another other features in Pointwise. It's a very powerful meshing program. But from here, yeah, you can grow your 3D mesh from this if you wanted to, using best practices. You can export this to Cart 3D, apply your boundary conditions to these things, these patches here. Like there's your inlet, so on and so forth. But it works pretty well. And yeah, that was maybe quick, but that was my solution to this problem, and it worked pretty well in getting a realistic engine model out of VSP in a pretty short order once you kind of had the geometry set up. So I'll stop there and take time for questions, or we've made up a few minutes on the schedule, if that helps.
No, that's